In 1859, Joseph Bazalgette was handed an impossible task: build a sewer network for London. Not for the 2 million people living there at the time, but for 4 million who didn't yet exist. The brick-lined tunnels he designed, with walls up to 3 feet thick, were condemned as wasteful excess by critics who couldn't see beyond the immediate need. Today, 165 years later, those same tunnels carry the waste of 9 million Londoners. The critics are long forgotten. Bazalgette's sewers endure. London in the mid-1800s was drowning in its own filth. The Thames had become an open sewer. Hundreds of cesspits overflowed into streets and basements. Cholera epidemics killed tens of thousands. In the summer of 1858, the Great Stink forced Parliament to abandon Westminster. The smell from the river made the building uninhabitable. Politicians who had delayed sanitation reform for decades suddenly demanded immediate action. Bazalgette, chief engineer of the Metropolitan Board of Works, had been preparing for this moment. His proposal was radical. Most engineers suggested building sewers sized precisely for current demand. Economical, practical, buildable within budget. Bazalgette refused. He calculated population growth trends, projected industrial expansion, and then doubled his estimates. If London held 2 million people in 1860, he would build for 4 million. When colleagues protested the expense, he simply replied that the work would be done once, properly, or done again improperly within a generation. There would be no second chance. Construction began in 1859 along the Thames embankment. The main sewer lines would run beneath new riverside roads, requiring excavation through London clay to depths exceeding 20 feet in some sections. Bazalgette specified brick construction throughout. No cheap alternatives. No experimental materials. The contract called for 318 million bricks, each one inspected, each one laid in courses designed to resist crushing loads and water pressure that might not be tested for a century. The tunnel walls were built between 2.5 to 3 feet thick. Contemporary engineers calculated that 18 inches of brick would provide adequate structural strength for sewers of this diameter. Bazalgette added another 18 inches. Not because he mistrusted his calculations, his mathematics were precise, but because he refused to trust the future to remain stable. Ground settlement, unexpected loads, deterioration of mortar, flooding beyond design parameters. These were uncertainties. No formula could eliminate. Extra thickness was insurance. It cost more. It would save everything. The bricks themselves were no ordinary construction grade. Bazalgette demanded engineering bricks fired at high temperature for maximum density and minimum porosity. Each batch was tested for compressive strength and water absorption. Rejected bricks were common. Quality controlled every stage from kiln to tunnel wall. The mortar specification was equally uncompromising. Portland cement mixed with hydraulic lime, capable of setting underwater and resisting sulfate attack from sewage indefinitely. This was expensive mortar. It remains chemically stable today. Foundations extended deep into the London clay, where tunnels crossed unstable ground or former waterways. Bazalgette ordered mass concrete footings, essentially modern foundation practice, 50 years before reinforced concrete became standard. The concrete was laid in enormous volumes, hand-mixed on site, wheelbarrowed into trenches, and tamped solid. No machinery, no shortcuts, just labor, cement, aggregate and the main outfall sewers ran for miles. Northern lines from Wick Lane to Beckton. Southern lines from Deptford to Crossness. These were gravity systems, requiring precise gradients, maintained over distances, measured in tens of thousands of feet. Surveying teams worked with chains and levels, establishing benchmarks every few hundred yards. Tunneling crews followed, excavating by hand, shoring with timber, lining with brick as they advanced. Progress was measured in yards per week, not miles per month. Speed was never the objective. Permanence was above ground. Bazalgette constructed pumping stations at strategic points, Abbey Mills, Crossness, Deptford. These were not temporary sheds housing machinery. They were palaces of engineering, built from load-bearing brick and decorative ironwork, housing beam engines powerful enough to lift thousands of gallons per minute. The buildings were overbuilt by any standard, walls thicker than structural need, foundations deeper than soil conditions required, ornamental details that served no functional purpose. But Bazalgette understood that fundaments extended beyond structural integrity. Buildings respected by the public would be maintained by the public. Beauty ensured survival. The network grew section by section. Northern high level, northern low level, southern high level, southern low level. Each system independent, each built to the same uncompromising standard. By 1865, 82 miles of main sewers were operational. By 1875, the complete network exceeded 100 miles, not counting the thousands of miles of smaller branch sewers that fed into the system. Every connection was sealed, every junction was inspected, every section was tested under pressure before being declared complete. Critics continued to attack the expense. Parliamentary committees questioned the need for such robust construction. Contractors submitted alternative designs using thinner walls, cheaper materials, narrower tunnels. Bazalgette rejected them all. He had been given authority to solve London's sanitation crisis permanently, not temporarily. The Board of Works supported his decisions, even as budgets expanded beyond initial estimate. The final cost exceeded £3 million, an enormous sum in 1870s currency. Adjusted for modern values, the project cost over £600 million in today's money. For context, a comparable modern sewer project of similar scale would cost £2 to £3 billion and require replacement within 75 to 100 years. Bazalgette's sewers required no replace maintenance. Yes, inspection, cleaning, occasional repairs to joints or connections, but the primary structure remained untouched. The brick walls showed no signs of deterioration. The mortar joints remained sound. The tunnels, built for a population of 4 million, handled 6 million by 1900, 8 million by 1950, 9 million today. They were never overwhelmed. They were never inadequate. They simply continued functioning, decade after decade, as Victorian engineering intended. The system survived challenges Bazalgette could never have anticipated. The Blitz of World War II saw German bombs devastate London's East End, collapsing buildings, cratering streets, rupturing gas mains and water pipes. The sewers beneath sustained damage in several locations, but the damage was localized, repairable, never catastrophic. The 3-foot-thick brick walls absorbed blast forces that destroyed structures above ground. Repair crews entered the tunnels within days, shored damaged sections, laid new brick where needed, and restored flow. The network never failed completely. Sewage continued moving toward the outfalls even as the city burned overhead. Post-war reconstruction brought explosive population growth and industrial expansion far beyond Victorian projections. By the 1960s, London's population approached 8 million. Modern planners examined the sewer network, expecting to find a system strained to breaking point, requiring complete replacement. Instead, they found Victorian tunnels operating comfortably within design margin. Bazalgette's doubling of capacity had created a buffer sufficient to absorb 70 years of unanticipated growth. The tunnels required supplemental systems. The Lea Valley trunk sewer, for example, added in the 1930s, but the core Bazalgette network remained the backbone of London's sanitation infrastructure. Today, engineers study Bazalgette's work not as historical curiosity but as practical reference. Modern sewer design optimizes for current demand, plus a modest growth factor, typically 20 to 30 years of projected expansion. This approach minimizes initial cost and allows for adaptive management as conditions change. It also guarantees replacement within a human lifetime. Bazalgette's approach was the opposite. Maximize initial investment, eliminate future replacement, design for indefinite operation. The mathematics were straightforward. The courage to execute them was rare. The Thames embankments, built to house the main sewers, transformed London's geography. What had been mudflats and tidal zones became solid ground, supporting roads, gardens, and later the Victoria Embankment Underground Railway. The embankment walls themselves were built to Bazalgette's standards: mass concrete foundations, load-bearing brickwork, granite-facing blocks. They were designed to contain the river and support the sewers beneath, but they were built strong enough to support anything the future might require. Today, they carry 6 lanes of traffic, underground rail tunnels, fiber optic cables, water mains, gas lines. Loads and uses Bazalgette never imagined, but structures he built to accommodate. The lesson was not lost on later engineers. The Black Wall Tunnel, opened in 1897, used similar principles: thick brick linings, conservative safety margins, construction quality prioritized over speed. The same approach appeared in railway tunnels, underground stations, water supply aqueduct. Victorian civil engineering developed a philosophical consensus: build once, build permanently, accept higher initial cost, eliminate replacement cycle. This was not universal practice. Cheap construction existed alongside overbuilt infrastructure, but the most successful Victorian projects, the ones still functioning today, followed Bazalgette's model. Modern engineering has moved away from this philosophy. Cost-benefit analysis dominates project planning. Life cycle replacement is accepted as normal. Structures are designed for 50-year service lives, 75 if conditions are favorable. This approach spreads costs across generations and allows for technological improvement with each replacement cycle. It also means constant renewal, perpetual construction, recurring disruption. Bazalgette built sewers once. London has maintained them for 155 years. The math is compelling. The irony is that modern materials should enable even greater permanence than Victorian brick and Portland cement. High-strength concrete, corrosion-resistant steel, polymer composites. These materials outperform anything available in the 1860s, yet modern structures rarely last as long. The difference lies not in materials, but in intent. Victorian engineers designed for permanence because they had no choice. Replacement was economically and politically impossible once construction finished. Modern engineers designed for replacement because the system assumes the materials are better. The philosophy is shorter term. Bazalgette died in 1891, knighted for his achievements, respected by peers who had once called him wasteful. His sewers were already 30 years old, still functioning flawlessly, already proving the skeptics wrong. He did not live to see them carry 8 million people's waste, survive the Blitz, or become the foundation of modern London's infrastructure, but he built them knowing they would. That was the point. Not to serve his generation, to serve every generation after. The tunnels remain in operation. 3 feet of brick, laid course by course, inspected joint by joint, built without machinery, without computers, without modern project management, just mathematics, materials, and the conviction that engineering done properly lasts indefinitely. Today's London depends on decisions made in 1859 by an engineer who understood that the future arrives faster than anyone expects, and permanence costs less than replacement.